Before we move on to the next topic, I would like to give you some ideas about the classification of metal processing. It is difficult to classify the metal processing because there are huge variety. It is based on the criteria that we are interested in. And today I would like to focus on four types of metal processing. The first two would be the primary processing that can be divided into the casting process and the forming process. And the next two are the cutting and the joining processes. And in terms of metal casting, there are a range of metal casting processes starting from sand casting, gravity die casting, pressure die casting, and also centrifugal casting or rotational molding and so on. And in the area of metal forming, there are a range of techniques that has been used to change the metal shape by mechanical means. The conventional process that I will emphasize on is the sheet metal forming, forging, rolling, extrusion, and wire drawing process. And in the next category is the cutting process that involved electrochemical machining, electrical discharge machining, or the single or multiple point cutting and grinding. Finally, in the joining process that involve fusion welding based on arc welding, laser or electron beam welding. And in another type of joining process, which is more recognizable, is the solid state welding that need frictions. And the last one is the mechanical joining. But within this chapter, I would like to focus on these two types of metal processing. The first one is the casting process, and the second one is the forming process. Topic 6.3 Metalworking. And for the classification of conventional metalworking, there would be forging, rolling, extrusion, drawing, and sheet forming. As you can see from the picture over here, this is the schematic showing the forging process. What we have here in orange is a lump of metal that has been put in between the upper and the lower die that appear in blue, where inside showing the profile of die cavity. And once this lump of metal has been forged by applying the normal force against the die, small amount of the metal flow out through the flash, while the inside die cavity completely filled to give the final forging product. And for the rolling process, the metal slab has been rolled from left to right to reduce the thickness to the desirable size, and this is through a set of rolls that revolved in the opposite direction. And for the extrusion, you can see the setup over here. The metal piece is placed inside the chamber, while the extrusion die attached onto the right end. The compression force is applied from the left-hand side to push the metal piece to flow through the die opening, and that we will have the smaller diameter of the bar. And for the last example is the metal drawing, and you can see that we have similar setting of the die, but with a smaller size of the die opening. This is the drawing die, but then we're not applying the compression force, but the tensile force at the right end. And this is to pull the metal, giving a smaller diameter of the wire, for example. So the key properties in metal drawing is that the materials have to have good ductility and work hardening. So the definition of metalworking is the working operations that change the metals into desirable shapes by means of applying the mechanical forces. If we classify the metalworking by temperature to do the operation, we can classify into two groups. The first one is hot working. That is, the operation is done at the temperature higher than 60% of the melting point of the metal. And for cold working, the operation is done at the temperature less than 30% of the melting point of the metal to be formed. So in hot working, we introduce the deformation and plus the temperature, and the result we will get the recrystallization that will directly affect the metal microstructure and also its properties. And then for cold working, we introduce the deformation at the temperature of less than 30% of melting point, and so it will give work hardening or strain hardening. That means the metal will get stronger and harder. So from this point of view, we have to choose whether we're gonna do hot working or cold working for the metal piece. And for hot working, it's normally done in the primary process because we introduce the deformation and temperature in order to reduce the big lump of metal into smaller size that is appropriate for further secondary processing. And for the secondary processing, normally done in a cold working condition so that we can increase the strength, hardness, or other properties that's suitable for applications that has been designed at the first place. Now let's have a look on this diagram. If we start with the metal with equiax microstructure, as you can see from this point, and to the right, if we increase the amount of cold work, that is, we introduce the deformation into the metal piece, for example, rolling or fudging. Once we apply the force, the grain has been deformed into the working direction like this. Previously, the grains are looking like the globular or equiax grains. But then after cold work, all the grains have been deformed, look like the pancake. Now in this graph above here, we can see the variation of mechanical properties such as hardness, strength, and ductility with increasing cold work amount. As you can see over here, the hardness and strength increase gradually with increasing amount of cold work. On the other hand, the ductility reduces gradually with increasing amount of cold work. But then for the microstructure, the grain size reduces just a little with increasing amount of cold work. Now, after deformation, if we introduce the temperature to the metal, we can see the microstructure has changed gradually towards increasing temperature over here. The previous elongated grains has changed into recrystallized grain towards the recrystallization process like this. But if the temperature is too high towards the end of this diagram, then the metal microstructure will be subject to grain growth. So now let's have a look at the relationship of the mechanical properties up here. And within this diagram, it can be divided into 3 regions from the dashed line over here. The first region is the recovery. That is, the metal product has been subject to temperature, but the temperature is not too high, it's less than 30% of the melting point. So the metal product can retain its hardness and strength at the high level in this recovery range. So we can probably see the old grains as previously observed in the cold working condition. And now if we increase the temperature even more into the recrystallization range, the microstructure starts to change as the stress point, as you can see over here, will initiate the nuclei for further grain recrystallization, as you can see over here. When the temperature proceeds into the higher level, all the grains are recrystallized into smaller grains, and these new smaller grains are ductile and free from stress. Therefore, this makes the hardness and strength drop sharply towards increasing temperature in the recrystallization range. But then if we have a look on the ductility increases significantly within this range, and that means when we apply deformation and temperature to obtain recrystallization, the grains are smaller and soft. And that means the metal product is ductile and it is ready for further operation, either hot working or even cold working. Therefore, this is the point of hot working, that we apply deformation temperature to obtain recrystallized grain. But beyond this point, we have to be careful because too high temperature will result in grain growth in the microstructure. Then the last grain microstructure is prone to be brittle and is not suitable for cold working. Therefore, we have to limit the range of hot working temperature to be within 60% of the melting point of the metal piece. Otherwise, the hardness and strength will reduce even more against the increasing grain size that is not suitable for further working operation. So to this, we can conclude that for hot working, we obtain recrystallization to the metal microstructure, and once we apply the temperature, the yield strength of the metal decreases Therefore, we can apply lower working load for each operation. Therefore, we have low load capacity machine. But at high temperature, we normally obtain oxidation. The metal surface will subject to oxidation. So the undesirable metal oxide formed on the surface that need to be get rid of in the next process. The metal product obtained after hot working operation will possess low strength and high ductility as the result of crystallization. So the hot working operation is suitable for primary processing that break down the big lump of ingot into smaller sizes that ready for secondary processing. For example, to the co-working operation. Then the summary for co-working. No recrystallization takes place because the temperature is lesser than 30% of the melting point of the metal, and that the working operation is done at low temperature and normally at room temperature. The yield strength of the metal is still high, so that require high load capacity for the machine to introduce the high load in the working operation. And at low temperature operation, there will be no oxidation. So the surface finish of the metal piece is good enough if we apply sufficient lubrication. And the final mechanical properties of the metal piece after co-working. That is, the metal piece will have high strength that is suitable for engineering application, but with low ductility as a result of work hardening or strain hardening. The first metalworking operation that I will be talking about is the forging. Forging is the working of metal into a useful shape by hammering or pressing. As you can see from the cross-section of the final product in this picture, the products are called forgings. And the forging is the oldest of the metalworking arts that is called the primitive blacksmith. And for the forging operation, it can be classified as open die, closed die, and impression die forging. As you can see from this picture, in picture A over here, showing the open die operation, the upper and the lower die, with the metal lump in between. Before we start the forging operation, this lump of metal have the original diameter of D and original height of H0 once applying normal force on the top of the die. The metal piece has been deformed, changing to the diameter of D1 and the height of H1. And then further forging operation will increase the diameter with reducing height. And you can notice that by using the open die operation, we receive the barreling effect along the side of the metal piece. This open die forging is normally done in the hot working range and normally with big size of metal piece. Picture B shows the closed die forging operation. As you can see, we also have the upper and the lower die. But by using the closed die, the metal piece will be squeezed inside the die cavity, but with small amount of metal piece squeezed out after applying the normal force against the die. And by applying the normal force, the metal flow in the perpendicular direction to the applied force. And further operation, the metal flow to fill the die cavity. So the closed die forging operation is normally applicable for smaller size of metal product. For the last type of forging operation, we have the impression die forging. And for the impression die forging, we can obtain the forgings with accurate dimensions. We also have the upper and the lower die, but with the introduction of flash, as you can see over here. The flash acts as safety valves and to keep the metal that has been squeezed out from the die cavity. And also, with this thin section over here, it will produce high pressure that help the metal to fill all the recesses within the die cavity. So this picture on your right hand side showing the action of the flash that help the metal to fill all the recesses within the die cavity. First, if you look over here, is the cross-section of the upper and the lower die, and within the die having the profile of the final metal product with the flat lens over here. And once the metal piece has been forged, small portion of the metal has been squeezed out into the flash lens. This will help to create high pressure for the metal to completely fill all the recesses in the die cavity. After that, we have to get it out of the flash by trimming out, and then we get the final component like this. Then finally, if you notice the cross-section of the forging once again, we can see that the metal grain will flow normal to the applied force, which is in the vertical direction. This metal flow or microstructural texture is the nature of the metalworking process, that the metal grains are aligned according to the working direction. And also the texture obtained will give the strength to the metal piece in the direction of grain alignment. This picture, as you can see, demonstrates how hot forging has been operated. We need the big machine to do the operation. And you can notice that this metal piece is huge according to the size of the worker over here, and therefore the operation needs high temperature, and that is in the hot forging operation. Therefore, this big metal piece has been heated up to the temperature over than 60% of its melting point in order to obtain recrystallization that will bring down the yield point of this metal piece and restore ductility to allow the forging operation much easier than doing it at room temperature. And this hot forging operation has been done using the open die forging, as you can see, the upper die and the lower die. At the other end, the machine will rotate these big columns that the reduced section towards the end can be obtained. And if we classify the forging machines based on its operation, there are 4 types of forging machines. First is the board hammer, second is the steam hammer, third the crank press, and fourth the hydraulic press. Within this diagram, you can see the broad hammer over here. The metal piece will be placed between the upper and the lower die that is attached onto the anvil over here. The force is applied on the upper side by rolling of the board and the ram up, and once the board is released, the ram will move down to apply the force onto the upper die through the metal piece. And next type is the steam hammer. As you can see, the metal piece is again pressed between the upper and the lower die on the anvil. On the upper die is attached with a piston that can move up and down according to the steam. And once it's going down, it's going to press in the vertical direction to the metal piece. The third one is the crank press. As you can see, the metal piece is placed between the upper and the lower die, and the upper die is attached to the crank. And on the rotation upwards, it will bring the upper die in the same direction, and once on the onwards direction, the upper die will press on the metal surface, resulting in metal forging operation on the bottom stroke. And here we should note that the crank press not actually apply the vertical load onto the metal surface, but it squeezes the metal along the side before pressing the metal into shape. The last one is the hydraulic press. Once again, the metal piece is placed between the upper and the lower die, but this time the upper die is attached to the hydraulic that can smoothly apply the force onto the metal piece. And by using hydraulic press, we can obtain the metal piece with deeper penetration and more homogeneous microstructure across the section. In comparison to the hammer forging up here, the force applied faster than the hydraulic press, and as the forging is very quick, so the penetration of the force through the metal piece is not as good as the one that obtained from the hydraulic press. Therefore, for hammer forging, it is normally applied for small forgings with high production rate. And for forging operation, there are several steps that we have to go through. First, the rough forging or rough shaping. Then, next step is finishing. And finally, trimming out of the flash. For example, if we start with a bar metal that finally will produce the connecting rod that you can see down here, there are several steps of the forging that we have to go through. First is the rough shaping. That makes some of the metal over here flow towards the end, so that next step we can flatten the metal bar and provide larger section over here. Then towards the finishing step, we apply more details onto the metal surface. and finally giving the finishing, then trimming out of the flash to give the final product of the forging, as you can see over here as the connecting rod. And you can see that forging requires several steps to get through the final product, and within each step we gradually change the metal shape towards the final dimensions. And by doing so, we gradually change the metal flow patterns or the metal texture into the metal product and giving the strength as well. And next I will give you the example of simulation of the forging in the first step. You can see that rough forming is first introduced, so the metal piece having reduced height and greater diameter. And in the next step, the forging operation introduced more details onto the metal surface, like you can see over here. In the finishing step, the final detail has been introduced, and you can notice that the flaps form around here that will be get rid of in the final step. Next metalworking operation is rolling. Metal rolling in a hot work operation is classified as the primary process. As you can see in this process, we're starting here from the big metal slabs that are heated in the step furnace to the correct rolling temperature, which is around 1250 Celsius. And next, the slab will be going through the roughing mill, as you can see from the roll stand over here. The working rolls on the top and the bottom, and the backing roll supporting the working rolls. This set of the rolls is called a stand. And once the slab passing through a roughing mill, the slab of original thickness around 220 mm can be reduced down to 30 mm. And as the thickness has been greatly reduced, so the length of the slab has been increased significantly. For example, if the original length is 11 meters, by going through the roughing mill, the length can be increased up to 80 meters. And that requires coiling of the metal plate, first to save the space of metal operation, and second to preserve the heat that's still contained in the metal coil for further operation. Then in the next step, the metal plate is uncoiled and cleaned to remove the mill scale that taking place on the hot operation on the metal surface. And this can be done by jetting the water to remove the scale on the metal surface before going through the finishing mill. In the fourth step, we have a series of stands. Over here you can see 1, 2, 3, 4, 5, 6 stands of rolls that will help to continuously reduce the metal thickness once passing through a series of roll stands. And to this, the extreme forces are applied to the rolls, and that roll the steel to a thickness of between 16 mm down to 1.8 mm. For example, the rolling speed is around 120 km per hour at the end of the hot roll milling. And once again, if we notice that thickness of the sheet is reduced down, for example, to 2 mm, the sheet will now have very long length that increases from 80 meters in the previous step to 1,300 meters once passing through this finishing mill. And that, of course, the next step we will need coiling of the metal sheet. But before then, we need to cool down the sheet in this step. The sheet is cooled before it is coiled, and this can be done by laminar cooling of the water. This laminar water cooling will bring down the metal sheet temperature to about 600 Celsius prior to coiling. And once finishing, the hot roll sheet is now sent to the customer or can be cut into length for further operation in the secondary processing. Remember that the previous operation is done at high temperature as in the hot rolling operation. Therefore, the surface of the metal sheet normally has the oxide scale. And then for the finishing products, we need to remove that oxide scale through the cold rolling operation. In the cold rolling, the metal sheet will make thinner. For example, if it's starting from 6 mm thick, we can make the metal sheet thinner and smoother by passing through a series of roll stands like this. So the cold rolling takes place in a tandem mill with 5 stands under one another, as you can see from this picture over here. And by doing so, the tension applied on both ends are very high. And in the next step, the steel sheet can be rolled down to about 0.3 millimeter thick. And if we're thinking of rolling down to about 0.6 millimeter, the strap of the coil will be up to about 4 kilometers long, which is very long, so that coiling is now applied to the operation. Now in the next step, the cold rolled sheet is very hard and brittle because in previous step there was no temperature involved. Then the work hardening has been introduced onto the metal sheet, giving it hard and brittle. Then it must be annealed to restore its formability, that is, to give in the ductility and lower the yield strength. This operation is in the continuous annealing line. The temperature applied is up to 850 Celsius. In the next step, we have to restore the strength to the metal sheet by quenching it at the rate of 1000 Celsius per second. And this is according to the type of the metal sheet. In this case is the steel sheet. After quenching, the sheet is usually tempered at low temperature to restore the ductility. And for tempering, this is done at lower temperature than annealing. It is in the range of 200 to 500 Celsius to make the hardened steel tougher. Then finally, the steel sheet is coiled to produce the cold rolled sheet that is ready for the sheet forming operation in the next step. Alternatively, we can go through another route over here that we apply the coating onto the steel sheet for some specific condition that corrosion resistance is required. So in this step over here, the anneal and quenched steel sheet can also be carried out in the metal coating line. In the hot dip galvanizing, the strip then passes through a molten zinc bath at a temperature of around 455 Celsius before being cooled down in the water like this, and then finally coiled to produce the steel sheet that has been hot dipped galvanized, as you can see over here. And for customer choice, hot dip galvanized steel sheet can be after treated by painting by going through this operation before it is delivered to the customer for further processing. The next metalworking process is extrusion. In extrusion process, a block or billet of metal is reduced in cross-section by forcing it to flow through a die orifice under high pressure. And if you notice in this picture, you can see that the billet is placed in the chamber. The ram forced the billet in the horizontal direction, making the billet to flow through the die opening and make the extrusion with a smaller diameter in comparison to the billet itself. And the picture on your left hand side showing the sections of extrusions. They are, for example, aluminum sections for windows and doors, as you may be familiar with, as they are used in the construction of houses and buildings. And the extrusion products are called extrusions. The major force that is applied for this metalworking operation is the compressive force, and that will make the billet stronger and tougher. All the properties that have been obtained from the casting process in the previous step and be closed, and that is good for mechanical property improvement. As mentioned previously, that the metalworking can be done in hot working or cold working conditions. It is the same as in extrusion. If the extrusion is done at high temperature, it is called hot extrusion, and that is suitable for reducing the billet size from the big size down to the smaller size that we need high temperature to lower down the yield strength of the billet. On the other hand, for cold extrusion, that means the operation is done at room temperature. So the cross-section of the billet before performing the extrusion must be small to allow the extrusion operation at room temperature. The extrusion process can be divided into two types. The first one is the direct extrusion, and the second one is the indirect extrusion. And this depends on the movement of the ram in relation to the billet movement. So for the direct extrusion, you can observe from the diagram over here, showing the cross-section of the extrusion setting, we can see that the billet is placed in the container. And the container must be strong, having high strength that can resist the force towards the billet flow according to the ram movement. The die is placed with the die opening having the cross-section similar to that of the extrusion. The die is attached to the die holder. Both die and die holder must be strong and tough in order to resist the billet flow as a result of ram movement during extrusion. The ram is forced in the horizontal direction to push forward the billet to flow through the die opening to make the extrusion. So, for direct extrusion, the ram is moving in the same direction to the extrusion. For the indirect extrusion, as you can see from the cross-section of the setting over here, the billet is placed within the container with the closure plate end. That is to resist the force applied by the ram on the other side. For indirect extrusion, the ram is hollow and pressed against the die, and that is to make the billet flow through the die opening, making the extrusion. So the extrusion moves in the opposite direction. So for indirect extrusion, the ram is moving in the opposite direction to the extrusion. The key properties that require for metal extrusions are ductility and not too much of high strength, for example, aluminum and steel. So in the case of high strength alloys, we have to increase the temperature in order to bring down the yield point that make the metal softer, that the metal will experience recrystallization to make the metal more ductile as a result of finer recrystallized grains. And one important thing is that good lubrication is required in the extrusion process. That will help to reduce the friction along the billet container and also between the billet and die and the billet and the dummy block. And that will allow good flow pattern of the billet through the die opening without the dead zone of the metal flow around the die entrance that will make extrusion defects later on. The next metalworking operation is drawing. Metal drawing involves reducing the diameter of a rod or wire by passing through a series of drawing dies or plates. As you can notice from this picture, from right to left is the direction of the wire drawing. And here, the picture on the top showing 3 drawing dies that aligned in the same direction according to the bore diameter and the speed of the wire drawing. The cross-section of the wire reduces after passing through each die. So the wire drawing operation is done continuously. Picture in the middle here showing the cross-section of the drawing die set up. Towards the drawing die entrance, it is tapered to allow the metal flow to obtain the drawn wire with reduced cross-section. Unlike the extrusion, the operation is made according to the tensile force. So the materials properties required for wire drawing is to have good ductility and significant work hardening exponent. For the drawing die, as you can see from the cross-section on your right-hand side, up here is the die entrance that you can see the cross-section of the bell and the approach angle, the carbide nib that is housed by the steel casing. The opening here determines the cross-section of the wire. So the drawn wire can be seen like the products in this picture, and smaller diameter drawn wires can be coiled. This type of products are used mainly in the construction or any other engineering applications. The last metalworking operation that I will be talking about is the sheet metal forming. The process is carried out in the plane of the sheet by tensile forces with high ratio of surface area to the thickness. And with the operation, it can produce a variety of complex three-dimensional shapes. As you can see from the sketch of sheet metal forming operation over here. For the first operation, it is blanking, where we put the metal sheet between the clamps on the top and the bottom. And once we apply the force through the cutting die downwards here, it will produce fracture on the metal sheet at around here, that breaking out the sheets into blanks. Hence, the operation is called blanking. The next sheet metal forming operation is stretching. The metal sheet is clamped by the blank holder and the die. On the operation, the punch underneath the metal sheet moving upward and to form the dome or the curved surface like this. Next is the deep drawing operation. The metal sheet is now again held between the blank holder and the die. The punch on the top moving downwards against the metal sheet, and on the downwards movement, we can obtain the cup with its bottom diameter similar to that of the punch diameter. The next operation is coining, where the metal sheet is pressed by the coining tool. The next process is stamping that produced the shallow profile. As you can see from the picture above here, the shallow profile is formed by the movement of the punch downward against the die ring and the blank holder that keep the metal sheet along the edge. The next one is ironing. That is quite similar to deep drawing, but the thickness of the metal cup has been reduced once operating when the punch is moving downwards. In folding operation, we have two sets of die that clamp the metal sheet in both ends. One is stationary and the other one moving upward to give the folding operation. And for the bending, we can have the V die and the punch in a V shape that folds the sheet into the V shape by moving downwards. Alternatively, we can use roll forming of the sheet by putting the sheet between the upper and the lower rolls. And finally, for wiping down the flange, that is, one side of the metal sheet is clamped, while the other side having the flanking tool moving downward to bend the sheet. So there are a variety of complex three-dimensional shapes that can be produced by the sheet metal forming that depend on the tool setting, the profile of the punch and the die, and also the movement of the punch. For the sheet metal forming, as you can see, good lubrication on the metal sheet and the die is required in order to preserve good surface condition of the metal sheet after sheet forming operation. And in this picture here showing the materials used most commonly for the major vehicle structure components in the automotive. And from the picture here showing a variety of metal parts that have been formed by sheet metal forming. First, if you notice here, we have the aluminum that has been subject to sheet metal forming to form the hood, the roof, deck lid, and body side outer that made from steel and also have been subject to sheet metal forming process. The last example are the fender and the door outer that's made from baked hardened steels by sheet metal forming.